We'll conclude this unit with two lectures describing how certain atomic properties exhibit systematic trends across the periodic table. In this lecture, we'll talk about what we mean by size, the physical factors that govern it, and the periodic trends. Then we'll look at how these trends are modified when we form ions. We've already seen how the shape of the periodic table rises from the filling of atomic orbitals and how elements in the same group typically have closely related electron configurations, which then gives them common properties and behaviors. So now we want to look at one example of this, the atomic size. Before we look at any trends, let's first talk about what we mean by the size or radius of an atom. Atoms are mostly space. You have a small nucleus and then the electrons occupy the orbitals around the nucleus. But remember from quantum mechanics, that orbital is a wave function that tells us about the probability of finding the electron in different regions of space. So you can't directly talk about the size of an orbital. Those wave functions actually extend out to infinity. There's some non-zero probability of finding the electron 5 feet away from the nucleus. Of course, that probability is minuscule, but the point remains those wave functions extend out to infinity. So a more reasonable definition of orbital size might be to pick an isosurface which contains some fixed percentage of the probability density. For example, how far out do we need to go from the nucleus in order to capture 95% probability of finding the electron? That is, that we have a 95% chance of finding the electron within that radius. Those sorts of arguments can be used and sometimes are used to define atomic size. Another possibility is to look at the distance between nuclei and simple molecules and try to infer atomic size from those. For example, in F2, the distance between the two nuclei is 128 picometers. This distance reflects the sum of the radii of the two atoms. And since it's a homonuclear diatomic, that is, both atoms are the same, we can just split that distance in half to determine the radius of each fluorine atom and get 64 picometers. As shown here, we could do the same thing for the other halogen atoms as the other atoms in group 16, and therefore determine the radius for chlorine, bromine, and iodine. For other elements, you can look at, for example, their solids and perhaps back out the size of the atoms based on the so-called lattice constants of the metal, which essentially tell us about the packing density and size of the repeating units in these solids. Any remaining unknown atomic radii can then be worked out by looking at simple compounds that contain, for example, fluorine with a known radius and some other element with an unknown radius, and we can eventually work our way through the periodic table and determine all the atomic sizes. Both these possible definitions are used in practice depending on the context. Here we're going to use the definition based on this particular one, working out the sizes from simple molecules. Before we can talk about the size trends, let's first look at the factors that govern atomic size. The first of these is principal quantum number. As we saw a few lectures ago, orbitals with larger n values tend to extend further from the nucleus, meaning there's a greater probability of finding that electron in those orbitals further from the nucleus. Because n increases as you move down the periodic table, you expect that size will also increase as you move down the table. You can see that in this example as we move from fluorine, chlorine, bromine to iodine, and you can see that the sizes are generally increasing as we move down that column. The second factor is the effective nuclear charge felt by the outer electrons, Z effective. Z effective is the difference between the total nuclear charge and whatever screening of that charge occurs due to the other electrons. The total charge Z depends on the atomic number, but of course the valence electrons typically only feel a fraction of that charge because much of it will be screened by the other electrons. Now as we move right across the periodic table, the nuclear charge Z is going to increase by +1 for each element. In contrast, the changes in Z effective across a period tend to be much smaller. The biggest screening impact comes from the inner electrons, not from other valence ones. And the number of inner electrons will be constant across the period. So the result of this is that Z effective increases as you move across the period. Z is getting larger, but the amount of screening isn't changing much. The larger Z effective is, that is, the larger the effective charge that's felt by those valence electrons, the more strongly they're going to be attracted to the nucleus. So that's going to have the effect of shrinking the atom. It's going to pull those electrons closer to the nucleus. So as you move right across the period, you're going to get the atoms shrinking. Now you might think there's also an increase in the electron-electron repulsion among the valence electrons because we have more and more valence electrons, therefore more repulsion. But that effect is weaker than the impact of the increasing Z effective. So overall, the size decreases as we move right across the periodic table. This figure shows the sizes of the various elements across the periodic table. When we combine the fact that these atoms generally get larger as you move down the table and smaller as you move right across the table, we end up finding that the largest elements are near the bottom left corner of the periodic table and the smallest elements are in the upper right corner of the table. Here's another representation of the sizes that makes some of these trends more obvious. For periods 1 through 3, we see that the size generally decreases as we move across the period. However, every time we start a new period, for example helium to lithium, neon to sodium, or argon to potassium, we get a large jump in the atomic size. And that's because we're starting to fill orbitals of the next higher principal quantum number. Now, as we saw when we were talking about electron configurations, things get a little more complicated for systems such as transition metals. And so you'll notice the trends are still generally true, but there are a lot more subtleties associated with them. And these simple intuitive rules break down a little bit. Let's try a practice problem. Order chlorine, germanium, and bromine from smallest to largest atomic size. Pause the video, attempt the solution, hit resume when ready. Okay, so chlorine, bromine, and germanium are here, elements 17, 32, and 35 on the table. So we know that as we go down the periodic table to larger principal quantum numbers, the atomic size gets bigger. So bromine is going to be larger than chlorine. At the same time, we know as we move to the right, due to the impact of Z effective, the atoms get smaller. So we expect germanium to be larger than bromine. Therefore, if we combine these two pieces of information, we end up with the final order that chlorine is smaller than bromine, which is smaller than germanium, which is answer B. Now that we understand the trends in atomic size for neutral atoms, let's take a look at ions. Cations are considerably smaller than their neutral parent atoms. You can see this from a couple of perspectives. First, cations frequently lose all of their valence shell electrons. For example, sodium loses its 3s electron to become sodium plus. This makes it isoelectronic with neon. So instead of having its outermost electrons in the n equals 3 shell, now it has its outermost electrons in the n equals 2 shell. So you can understand that that's going to be considerably smaller. From another perspective, cations have the same number of protons as their parent atoms, but fewer electrons. So there will be less electron-electron repulsion, and that means the electrons can occupy a smaller volume and move closer to the nucleus to have more favorable interactions with that nucleus. Here are some examples to show you this effect. From sodium to sodium plus, we go from 186 picometers to 102 picometers. From magnesium to magnesium 2 plus, we drop from 160 to 72. So proportionally speaking, it's an even larger drop. For aluminum to aluminum 3 plus, losing all 3 valence electrons, we have a proportionally even larger decrease in size. So you can see that actually the more electrons removed, the bigger the change in volume. This vanadium example makes this even clearer. Vanadium can form either +2 or +3 cations, and you can see that the +3 cation is somewhat smaller than the +2 one. In contrast, anions are considerably larger than their neutral parent atoms. You can think of this from the perspective that we still have the same number of protons, but we now have more electrons. So there's going to be more electron-electron repulsion, and that's going to cause the electron cloud to expand to reduce that repulsion. So for example, from oxygen to oxygen 2-, we go from 73 picometers to 140 picometers. Fluorine to fluoride, we go from 71 to 133 picometers. Let's try a practice problem. Arrange P3-, aluminum 3+, and Mg2+, from smallest to largest size. Okay, so we have phosphorus 3-, aluminum 3+, and magnesium 2+. So first off, phosphorus is an anion, so that's going to get larger than its parent size, and it's going to be considerably larger because it's a threefold anion, isoelectronic with argon. In contrast, these other two species are cations that are isoelectronic with neon. So we know the phosphorus is going to be the largest. If we now compare the aluminum and magnesium, we know that the aluminum has a greater positive charge. It's lost more electrons, so we expect that there's less electron-electron repulsion and that it can hold its electrons more tightly, shrinking its size further. And so overall, we expect aluminum 3+ to be the smallest, then magnesium 2+, then phosphorus 3-. To summarize, for neutral atoms, we saw that the radius tends to decrease as you move across a row of the periodic table from left to right, and that's because the effective nuclear charge, Z effective, is increasing. As you move down a column of the periodic table, the principal quantum number and therefore the orbital size is increasing, so the atoms get larger. This means that the smallest atoms tend to be in the top right part of the periodic table, and the largest atoms are down near the bottom left. When it comes to ions, cations are smaller. Partly you can view that from the fact that they have a smaller effective principal quantum number because they've typically lost their valence electrons. You can also view it from the perspective of the fact that the nuclear charge hasn't changed, but they have fewer electrons. That means there's less electron-electron repulsion and the cloud can contract. In contrast, for ions, you have the same nuclear charge but more electrons, so you're going to have greater electron-electron repulsion, and that causes the electron cloud to expand.